possible. If all of this seems a bit too abstract, well, that's because it is. We are covering the topics from the REST dissertation, but essentially we can split the uniform interface constraint into its subcomponents. And these are the identification of resources, the manipulation of resources through representations, self-descriptive messages, and then probably the most important one, which is HateOS, which stands for Hypermedia as the engine of application state. So let's cover these components of the uniform interface one by one. A key component of REST is a resource, and a resource is any information that can be named. This could be a document, an image, a collection of resources, a physical or abstract object. It doesn't really matter because a resource is what we say it is. Now, one important quality of a resource is that we have to be able to identify it, and a resource has to be uniquely identifiable. And for this, we use the concept of a URI, which stands for Uniform Resource Identifier, and this concept is fundamentally different from a database identifier, which is how we identify some row in the database. A Uniform Resource Identifier is how we identify a specific resource inside of our REST API. So let's look at an example. Let's say we have a resource identifier called habits. This represents a collection of individual resources, and we can probably guess this from the name of the resource. But if we append a specific identifier to the habit, let's say H_12345, now this becomes a URI for one resource instead of the entire collection. The value we add here may or may not be the database identifier. It could be derived from a couple of fields that we store in the database, but essentially it identifies one resource inside of our system, and this allows us to expose some behavior on this resource. For example, if we now introduce an HTTP method, in this case get, this becomes a request for fetching a single resource from our REST API. We can alter the semantics of a given request by changing the HTTP method. For example, a post is used for creation, a put is used for updates, and so on. But what's important is that we are always referencing a URI to identify the resource. Another thing to understand is that a resource is conceptually separate from its representation. The representation is what we return to the client for a given request, but it's not the same thing as the resource itself. The representation only captures the current state of the resource at the time of the request, and it may change by the time that we return the request to the client. The representation may or may not include some metadata about the resource, and a good example of this is including hypermedia links together with the representation. The representation itself could be returned in some standardized format. Popular choices are JSON and XML. And this brings us to the next component of the uniform interface constraint, which is the manipulation of resources through representations. The client has to be able to use the representation that it has available to manipulate the resource, which means the representation needs to contain enough information in order to facilitate this. There are two ways of how we could drive manipulation, either using URIs, where the client is responsible for structuring the respective requests, or we could use HateOS or Hypermedia to send back the available Hypermedia links which represent the operations that the client can perform. The next aspect is self-descriptive messages, which in practice means that each message, either a request or a response, has to contain enough information for us to be able to process it. Other than the representation of the resource and the URI, we also facilitate this using HTTP methods, which carry different semantic behavior based on which method we use, and we can also use various media types to implement content negotiation between the client and the server. Finally, we have HateOS, which is short for Hypermedia as the engine of application state. And this is probably one of the most important RESTful constraints because of the rich behavior that it can introduce to a RESTful API in terms of how you expose functionality to the client, how you render the client interface, how you apply business rules which can change dynamically at runtime. But unfortunately, in most real-world APIs, you will rarely see Hypermedia implemented. And I think this is a shame, and I hope that by the end of this course you will understand the value of HateOS. The goal of HateOS is to drive how to consume and use the API. We do that by transferring a set of links that determine the operations that the client can perform on a given resource. This effectively makes our API self-documenting because the client doesn't need to understand how to structure a request and send it to the server. It can just look at the Hypermedia links and figure out what are the available options. So let me give you an example. Here's what an API response that supports HateOS might look like. This is a representation of a given resource returned by a RESTful API, and you can see that the response contains a links property, which is an array of individual hypermedia links. Each link contains a fully qualified URL representing where you can send the next request to. It also contains the HTTP method determining the semantics of this request, and then there is a description of the hypermedia link explaining what this operation represents. So in this example, we have a GET request to this URL to obtain this same resource, which is why it's called self. You can also see that the fully qualified URL is respecting the data shaping arguments represented in the fields query parameter, which determine the format of the API response. Then there is an update link for updating this resource, a delete link for removing this resource, and an upsert tags link, which gives us a URL that we can use to upsert some tags to this resource. And this can be helpful for categorization, but more on this later when we jump into the implementation. The next REST constraint is the layered system constraint, which says that we can compose a system out of multiple layers, and all of this should be transparent to the client. In other words, the client shouldn't be aware of the existence of many layers inside of our system. This allows us to create a composable architecture, which can make our system more scalable, and we can introduce components like a cache, a proxy, an identity server, and the client shouldn't be aware that any of these components exist inside of our layered system. The obvious trade-off here is that we get increased latency, because now we have multiple components that need to communicate with each other in order to satisfy a given API request and return a response to the client. And the last REST constraint, which we aren't going to spend a lot of time on, is the code on demand constraint. It states that the client functionality can be extended by executing some code that we can return from the server. This could, for example, be a script that we can download from the server and run on the client side to extend the behavior, but in practice, this isn't really implemented, and this is the only optional REST constraint, and we will not be implementing it inside of this course. By now, you should be able to understand what a REST API is, at least conceptually, and you should be able to understand the REST constraints. For an API to be RESTful, it has to conform to all of the REST constraints, except the optional ones, obviously. But this is really important if we want to be strict about what a REST API is. And because this is the topic of this course, this is how we are going to define a REST API or a RESTful API, however you want to call it. It has to conform to all of the REST constraints, including the hypermedia constraint. As I already said, most APIs in the real world don't conform to all of these constraints, therefore they are not RESTful APIs, but that does not mean that they are bad APIs, and we're going to discuss this in more detail in our next lesson. And the topic of our next lesson is precisely about this. I'm going to introduce you to the Richardson maturity model, which gives us a set of rules to determine the RESTful maturity of our API.